laws of the subatomic world are very, very different to those of the familiar large-scale universe. A huge outstanding question is when and why does the weirdness of quantum mechanics give way to classical physics? One answer to this question suggests that the entire universe is so much weirder than we imagined. Or should I say, the multiverse. One of the strangest features of the quantum description of reality is the idea of superposition. We can't describe the most fundamental building blocks of our universe with defined singular properties. Instead, they seem to behave as probability clouds of all properties they might have were we to try to measure them. Mathematically, this is encapsulated in the wave function of a quantum particle or system of particles. The best illustration of why we need to describe the quantum world this way is the famous double-slit experiment. We did an episode on it, check it out if you aren't familiar. But to summarise, a stream of photons or electrons or even molecules travels from some point to a detector screen via a pair of slits. These particles arrive at the screen distributed like the interference pattern you would expect from a simple wave. Quantum mechanics very successfully predicts this result by describing each particle's journey as a superposition of all possible trajectories. In other words, the particle simultaneously takes all possible paths, which means it passes through both slits. It tries out all histories between launch and landing, and those many maybe histories somehow interact with each other to determine the most likely final destination when a measurement is made. In a sense, different possible superposed histories appear to converge on one final outcome, but what causes that convergence? In the original Copenhagen interpretation of quantum mechanics, the act of measurement was thought to collapse possibility space into a single reality, at least with respect to the measured property. It collapses the wave function. That collapse signifies the transition between the quantum and classical realms. One of the founders of quantum mechanics, Erwin Schrödinger, found this ridiculous, and he proposed his famous Schrödinger's cat thought experiment to highlight the absurdity. It goes like this. A cat is in a box with a flask of poison. A machine containing a radioactive element is set to shatter the flask in the event that the radioactive element decays. If that happens, the cat dies. That radioactive decay is a purely quantum process, and so until it's observed, it exists in a superposition of states. It has both decayed and not decayed. But doesn't that mean that the entire macroscopic system attached to that quantum event is also in superposition? If so, then the cat should be simultaneously alive and dead until we open the box. But why can't the cat collapse its own wave function? And from its point of view, is the physicist outside also a quantum blur until the box is opened? And what about the entire rest of the universe that's not currently being observed by physicists or cats? Many adherents to Copenhagen now have a more sensible resolution to the paradox of Schrödinger's cat. It's that quantum superposition doesn't extend to macroscopic scales. It disappears when different quantum scale histories diverge. This is called decoherence. When the wave functions describing quantum systems overlap sufficiently, in other words they are coherent, it's possible to get interference in the double-slit experiment and spookily correlated quantum entanglement measurements. But when these systems interact with their environment, coherence is lost and parallel histories fall out of alignment. They can no longer interact with each other. By the Copenhagen interpretation, we might say that the universe chooses the final outcome of all of those histories. It doesn't exactly choose a single history, instead it chooses an end result, say particle location on a screen, or cat alive or deadness, based on those histories. If a larger number of possible histories lead to a given result, then it's more likely that the universe will select that outcome. The Copenhagen interpretation says that this selection happens in a fundamentally random way. The universe plays dice, even if the dice are weighted towards certain results. It is what we would call a non-deterministic interpretation because there's no underlying predictability behind the selection. However, there is another way to interpret the transition between the quantum and classical worlds. What if the wave function never collapses? If we can imagine a cat in a superposition of states, alive and dead, why stop at the cat? What if the family of possible states extends beyond the radioactive decay, beyond the cat, and includes the observer, and indeed the entire universe too? If we open the box and find that the cat is alive, it's because we are part of an entire quantum timeline in which the radioactive decay and subsequent poisoning never happened. But there's an equally valid timeline in which it did, and another version of us experiencing that. This sounds outrageous, but it's a very serious interpretation of the mathematics of quantum mechanics. It was proposed by Hugh Everett in his 1957 PhD thesis entitled The Theory of the Universal Wave Function. It's come to be known as the many worlds interpretation. To outline the idea without killing so many cats, let's talk about what this means in the context of the double-slit experiment. The Copenhagen interpretation tells us that the superposition of particle trajectories, of histories, merges into the single timeline of the observer's reality. Many worlds says this merging never happens. Those alternative histories continue, and we find ourselves in just one of those timelines. Which one? Well, they're all equally likely, but some look very similar to each other. For example, many histories lead to photons landing on the bright bands of the interference pattern, and very few to the dark bands. We tend to find ourselves in the more common families of histories. This is a pretty crazy notion. The many worlds interpretation invites the idea that reality splits into different branches every time quantum states diverge into different possibilities. For example, at every particle interaction everywhere in the universe. This would lead to an unthinkably large number of alternate timelines, or worlds, that contain all possible realizations of this universe since the Big Bang. It seems extravagant to propose uncountable, eternally branching universes just to get out of collapsing a wave function. It's like building an entirely new house to avoid doing the dishes. But remember, the Copenhagen interpretation itself proposes multiple worlds in the superposition of paths or properties of a quantum system. Both many worlds and Copenhagen create alternate realities. It's just that Copenhagen merges them into a single timeline with its wave function collapse. The superposition of states of many worlds can be thought of as overlaid histories, slices of a universal wave function that diverge from each other as the universe evolves, but none ever vanish. Many worlds may in fact be the more pure interpretation of the mathematics of quantum mechanics because there's nothing in that math that requires the collapse of the wave function. So many worlds is more economical in the number of unsupported concepts it adds to quantum mechanics, even if it isn't particularly economical in the number of universes it predicts. Now, Everett's idea wasn't taken too seriously when it was first proposed. That may have been in part because he wasn't a well-known physicist. He was just a graduate student who all but disappeared into military research at the Pentagon right after graduation. But another point of resistance must be the overwhelming existential crisis induced by the idea of near-infinite versions of oneself. Many worlds may imply that every possible version of you exists out there. You're just the one who happens to be experiencing this branch of reality. Every other possible life path, including those branching in different directions from every decision you ever made, may be just as real. In fact, each may be real in vast multitudes. There's no more evidence for many worlds than there is for other mainstream interpretations of quantum mechanics. And it is somewhat mainstream these days, with many noted physicists being swayed by its parsimony, its economy of ideas. But it remains an interpretation, and so although it is supported by the incredibly successful mathematics of quantum mechanics, it has not yet added a prediction that might distinguish it from other equally supported interpretations. Nor is it complete in its explanation. There are some ideas about what's really happening when these neighbouring coherent histories interact, or why the wave function translates to probabilities the way it does, but they are far from generally accepted. Unlike Copenhagen, many worlds is a deterministic interpretation. Any given timeline is a predictable chain of cause and effect. It explains the apparent randomness of quantum mechanics with a sort of observer bias. All possibilities are chosen at every junction, and we just happen to be seeing the one that happened in the branch that we occupy. That adds a second possible cause for philosophical unease. In a purely deterministic universe, what happens to free will? If we're going to make all possible decisions anyway, why sweat any given choice? Well, sure, but of all those countless future branches of reality, some are going to be pretty amazing. Think of it as a choose-your-own-adventure, and steer this version of you towards one of the more awesome many-world branches of space-time.